Okay, here's my homemade optics lab setup for the interference lab. Over here I've got a laser. There's a laser. It's a green laser. You can see the green there. And there is a thing that has different kinds of slits in it for the laser to go through. And then all the way on the other side of the room, I have a piece of paper taped on the wall with centimeter marks. And my camera is going to take nice videos of it, of what we get on the screen. And I have measured, and the distance between the slits where the light goes through and the screen is 270 centimeters. Okay, so that's basically the setup. I have a red laser also we can change out, and by dialing this thing here, we can dial this thing that says multiple slits, and there's lots of different settings on there, so we can change variables one at a time and see how changing those variables affects the pattern we see on the screen. So we can learn about interference that way, okay? Okay, so basically what we're going to do in this lab is we're going to shoot a laser through two openings, two slits. And a couple of the variables we can change are, one, we can change the distance between the slits. We can make the slits closer together or farther apart. And that variable we're going to call D, the distance between the slits, okay? And there's another variable we can change, which is how big the slits are themselves, the opening width. In general textbooks, I think Carlos also calls that A. So I can keep D the same and make a large A, small a, and I can keep A the same and make a large D or a small d. Okay, and we're going to look at both of those things and how they affect the interference pattern that we get. Another variable we can change is the wavelength of the laser. I have a red and a green laser, so the red one has a wavelength of somewhere about 700 nanometers, and the green one is about, say, 500 nanometers. So that's not a whole big difference. I can't double it or anything, but we can change it enough to see a difference. And in general, the wavelength of the lasers is about 100 times smaller than most of our openings, right, our A's, just to give you an idea. Okay. Okay, now I'm going to give you a tour of this little piece of equipment that we're going to use. It's the Pasco high precision diffraction slits. And the part we're going to mostly use today is the double slits. You can see here that there's a bunch of holes, and I can dial it around, and you can see that whichever one I have in that spot is the one that lets light go through. So you can almost see, if I dial it to the double slits, yeah, you can see there's a double slit. I can dial it to that one and they get closer together. Dial it there, and now you can see they're farther apart. Okay, so we're going to be changing this around, and you can see if I turn this, you can see the different values we have here. So here we've got an A of 0.04 millimeters and a D of 1/4 millimeter. These are all in millimeters. Here we've got A is 0.04 millimeters again, but we changed the D. So this is just changing the distance between the slits and keeping A the same. And then here are two with a wider A and the same two distances, bigger, fatter slits with the same two distances apart. So we can change two variables and keep the other two the same. Okay, so we're going to mostly use those. We also have this one here called a variable double slit that has a continuous, I can see, if you do that, see, I can dial it continuously to change the D, the separation between the slits. And you can see that it's keeping A the same the whole time. So that's a nice thing to just investigate how the interference pattern will change when we change D. Okay, so I'm gonna fire up both of these and show you the patterns on the screen, and we can talk about them a little bit. Okay. Okay, to start with, I'm going to shine the green laser through one of the double slits. You can see the little slit lit up green there. It's coming out and it's going over toward the screen. We've got a pattern on the screen. It's too dim to see, so I'm going to turn the lights out and we'll look at it. Okay, here's what we get on the wall on our screen. That's pretty interesting. We've got a bunch of little green lines, and they're kind of bright in the middle and they get dimmer toward the edge. What else do we notice? It looks like they're all of them are pretty much the same size, although they start getting dim and then they disappear, and then they kind of come back again dimmer, and then they disappear again, and then they come back dimmer. If I turn the lights all the way off, we could see it a little bit better. Let me do that. Make it a little darker. Okay, so now we see sort of a bright spot here, and then it disappears, and then another bright spot, and then it disappears. And what's going on? So what are we seeing? That's the first question. If you were in lab with me, if you were in lab with your lab groups, you'd be saying, well, what are we looking at here? You're thinking, okay, I want to see little bright and dark fringes, my interference fringes, right? That you learned about. So which ones are those interference fringes? Are they these little teeny spots, or is that one interference fringe and that's another interference fringe and that's another interference? How do we tell which one's which? So a good way is just to maybe play around, and a nice systematic way to play around is to maybe change one variable and see what happens. So let's just change one variable. The main important variable we're talking about in interference is the D, the distance between the two slits. So we can change D while keeping the A and the wavelength the same and see if that helps us figure out what we're looking at here. Okay, so I'm going to go over to the thing and I'm going to change D. What I'm going to do is make D big twice as big. So now D is twice as big as it used to be, and A is the same. So what changed? Well, it looked like that these little teeny fringes got closer together, and to me it looks like these gaps stayed about the same. And what you can try to do is maybe let's mark where the gaps are. See that pen? I'm going to put a mark there and a mark there. That's where those gaps are. And I'm going to go change D back again and see if that really is true, where those stayed the same. I'll try to do it without bumping it. And did it look like they stayed the same? Looks to me like those gaps didn't change, but the spacing between the little dots got bigger when I made D smaller. So what you learned from Carlos is that the interference fringes should change as you change the spacing between the slits. And as we change the spacing between the slits, that's what changed, not these things. So it seems reasonable to assume then, to guess, that these little tiny dots are our interference fringes. And we don't know what these gaps are right now. We're going to just assume that those are our interference fringes and these are some mystery gaps. Well, how could we investigate what those mystery gaps are about? We could do the same thing we did before. We could change one variable and leave the other one alone. So can I leave now my D alone and change, what other variables do we have? I could change the laser, but easier right now is I'm going to change the A, the width of the individual slits, and see That's just because that's something we have that's easy to change, and just as a first guess. So let me go do that and see what happens. Okay. Okay, so now I've changed A and left D as it was before. And you can see what looks to me is like these little spots, what we're now calling the interference fringes, are about the same distance apart as they were, but the gaps have now moved, so they're not where they used to be. They shrunk in, right? So what do you think? That looks kind of like that the A decides where those gaps are, and the D decides where these little fringes are. And for now, when we're studying double slit interference, we're going to be focusing on these little interference fringes, and we're going to have to put the gaps from the A's in the back of our mind, and you'll see more about those in next week's lab. For now, we're just going to kind of sort of ignore them, but always keep them in the back of your mind when you see things. Okay. Here's a little demonstration to help you visualize what's going on physics-wise with the double slit interference. I've got two sticks, and each one of these represents the laser light coming through one slit and the other slit, right? And we have white marks on them that are supposed to represent the wave. So like every white mark is the peak of a wave. So there's one wavelength, two wavelengths, three wavelengths. That's the peak of the wave. That's the bottom, the trough, another peak, and the same thing here. And the nice thing about lasers, and why we use lasers, is because they are coherent, meaning their wavelengths are in sync with each other. So they're coming out nice and lined up like this. If we use some other kind of light source, it wouldn't necessarily stay nice and lined up. Okay, so what we can ask is, well, what do we need to happen to get constructive interference? So if I think of these two lasers coming through these slits, and we get constructive interference when the peak of one wave lines up with the peak of the other wave. So for example, at the ends of the sticks, we can think of there being the peaks, and when the lasers travel right down to the center of the screen, it's symmetrical, and so they both travel the same distance and they line up, and we get a bright spot because the peaks are lining up. And then we can say, well, okay, where do we get the next bright spot? So we can rotate these, and okay, if we go to here, at this angle, now this laser, the peak of this laser is lining up with not the peak of that laser, so they're not in sync. They're not constructively interfering. So we have to keep going. Okay, now at that angle, we can see that this laser has a peak. This wavelength lines up with that wavelength, and that's going to be a bright spot where there's constructive interference. Okay, and we could do it the same on the other side. We could do this. And the next one is going to be way over here, where the second one lines up with it. Okay? So now what if I make my slits farther apart? So I'm going to make the two ends over here farther apart. Can you see that? Yeah. Okay. If they're farther apart, you predict how that's going to change the angle of my first bright spot. I'm always going to get a bright spot right in the middle because it's symmetrical. But where's my next bright spot? Is it going to be at a bigger angle or a smaller angle than when the slits were closer together, right? This is my D, the distance between the slits. Okay, so what do you think is going to happen? Make a prediction. We'll try it out with the little tool here. Okay, so I'm going to rotate these until they line up, and they didn't have to move very far to line up, right? It was a small angle compared to when they were close together. It took way over there till they lined up. Right? Again, here's a small angle. Not lining up, not lining up, not lining up. Now they're lined up. That's a big angle way over there. I put them farther apart, and I wait till they line up there. Now that's a shallower angle. So what that's going to mean is my fringes are going to be closer together here, whereas when the D is really small, there's my first fringe. There's one fringe and there's another fringe way over there. So that's what you're seeing when you're seeing interference patterns. So remember that in our laser actual experiment, the distance between the slits is hundreds of times bigger than the wavelength. So that would look like us putting these sticks super far apart, and therefore the angles that you need to get the different interference fringes are going to be teensy, which is why we have a big long distance between the screen and the slits. And you can see, and they're very close together. Those angles are very, very small. And we can use the small angle approximation, therefore. Okay, back to real lasers and real interference. Now what I'm going to do is I'm using the setting where I can adjust the slit separation D continuously by turning the dial and see how that affects the separation between the fringes, just like we did with the sticks. So now I'm going to turn D up, bigger distance, and you see the fringes get closer together, the angle gets smaller. And then if I turn it back down, a smaller D, the angle gets bigger, just like with the sticks. So that's what's going on. I can turn that up and down. And here again, the angles are very small compared to the sort of model we had with the sticks, but it's the same situation. If we say, for example, that this one is the center fringe where both rays travel the same distance, then this one over here would be the first one where the path difference is 1 wavelength, and then the next fringe is where the path difference is 2 wavelengths, and the next fringe is where the path difference is 3 wavelengths, etc. Okay, now I'm going to give you some patterns that you can use to take measurements and calculate things. So here we have a pattern where D is 0.25 millimeters, and to get the variable that I think we're calling Y, how far off the center you are, we can notice that they're all about the same spacing. So all we have to know is how much space there is between the center of one fringe and the center of another fringe. And I'm just going to let you use my crude centimeter scale. And so what I want to know is, what's the distance between two fringes? You can kind of just estimate it pretty carefully with my scale. It looks like it's about a little bit more than half a centimeter maybe. If you wanted to get fancier, you could say, well, this one's lined up with a black spot, so I'm going to count 1, 2, 3, 4, 5 fringes. 1, 2, 3, 4, 5 fringes in about 3 centimeters, and figure out, get it in units of centimeters per fringe. And that will be, the centimeters per fringe will be your Y with your m equals 1. If you want m equals 2, you can double that. If you want m equals 3, you can triple that, right? Because they're all the same spacing, so wherever the center is, we can just count the distance: 1 distance, 2 distance, 3 distance, 4 distance. Okay, so that's your Y. Your L we have as 270 centimeters, and you can figure out the wavelength of the laser that way. And now I'm going to change to a different D so you can take another measurement. Okay, now I've changed D to 0.5 millimeters instead of 0.25 millimeters. So that's twice as big. And again, you can count, you can measure the spacing between the fringes, being creative, knowing that those marks are 1 centimeter apart. So remember, we're not doing anything, we're not engineering anything that has to have some precision fit. So if we get a ballpark estimate for the wavelength of the laser, then we're happy. Okay, now I'm going to change the wavelength. I'm going to put the red laser on, and we'll see what we get. Okay, here's a pattern with the red laser, and I've still got my two marks for where the gaps used to be with the green laser. I haven't changed the A, and you can see now that both the gaps and the interference fringes themselves are a little bit farther apart. So you can make measurements here again using my centimeter scale. The screen distance L is still 270 centimeters. And now I'm going to change D again to this is 0.25 this is 0.25 millimeters for D. I'm going to change it to 0.5 millimeters. Okay. There is a D of 0.5 millimeters. It looks like the gaps didn't change, but these things got closer together. Okay. Take whatever measurements you need.